Okay, so now that we've gone over what a character table is, we can look at some examples of a character table and look at the different parts of them. So you can find lists of character tables on Web Campus. I have a handout there. Or you can look at any inorganic chemistry textbook or online. And again, for most problems, I will always be giving you the character tables that you'll need to solve them on the exam. So this is what we call the C3V character table. And that's always given at the top left of the character table. That's the point group. And the first thing is the list of the different symmetry operations that are in this point group. And these are listed as classes, so they're grouped together. And in this case, we have E, which is the identity, remember. We have C3, and we have two of them. We'll talk about what those two are, but they're two rotations that are similar, and hence they're in the same class. And then there's three mirror planes. These are vertical mirror planes, sigma V, and there's three different ones of them. So in total, there's one identity. We don't write the coefficient 1, but that's imagined there. Two rotations and three mirror planes. So we have a total of 6 operations for any molecule in the C3V point group. And then on the left here, we have names. And these are called Mulliken symbols. All these are the names of the different vectors, okay? If you're thinking about from a math standpoint, this is what it is. This is a vector in 3-dimensional space, right? Because what is the 3-dimensional space? It's the identity, rotation, C3 rotation, mirror plane space. Just like how you can have a 1-1 vector in X, Y, Z normal Cartesian space, 3-dimensional space that we think of, right, spatial. This is some symmetry space that also happens to be 3 dimensions, but it could be, multiple different dimensions, okay? So this is a vector, it's a 1-1-1 vector. In group theory speak, we call this an irreducible representation. If you're taking linear algebra, you would call this a basis vector. Why is it irreducible, or why is it a basis vector? It's orthogonal and it's normalized. And we'll show later on that all these vectors are orthogonal to one another. In other words, they're perpendicular. Just like X, Y, and Z are all perpendicular, these are perpendicular in the symmetry space, okay? And they're normalized, meaning that they're as small as they're the smallest whole number representations of these vectors, okay? So those are the different characters. Those are the traces of the matrix. Together, they make up a vector. And we have 3 vectors in these different rows. We'll call them irreducible representations most of the time from here on out. The last part of this is just naming these vectors, and that's the Mulliken symbol part. And so this is just a nomenclature that was developed just to keep track of some of the key components of these irreducible representations and give them a convenient name. Now, so you can see they're called A1, A2, and this one's called E, unfortunately. That was the nomenclature. This is not the identity E, this is the E representation. E irreducible representation. This is the identity E, the symmetry element, okay? And so there's a few more things. I've been using the word dimension. And I said this was a 3-dimensional space, right? Because that's 3 different classes of character tables. The word dimension is different than the word dimensionality, okay? And dimensionality, it's not something we'll use a lot, although there are some relationships we will use from it. And all dimensionality means is it is what is the character under the identity column, okay? So you'd say A1 has a dimensionality of 1. A2 has a dimensionality of 1. The E irreducible representation has a dimensionality of 2. We're just looking at this column. And then lastly, what we figured out earlier was that there's 6 symmetry elements in C3V. That's called the order of the point group, and that's just the total number of symmetry elements. So you're just gonna add up the coefficients in this top row there. So 1 plus 2 plus 3 is 6. And so lastly, I'm just going to list the rules for assigning Mulliken symbols. Again, this is a lot of this stuff in group theory. Starting out is like learning a new language. So these are just some language rules. It's nothing deep, and it's all arbitrary, of course. Just like language rules are pretty arbitrary. And so how does this work? Well, it's first based on the dimensionality. So if you have a one-dimensionality irreducible representation, it's going to be called either A or B. And it's going to be called A if it is symmetric with respect to the principal rotation axis, the highest order Cn. If it's anti-symmetric, meaning you have a -1 character, symmetric meaning you have a 1 character, you're going to put it a B. Okay, that's the Mulliken symbol. And then if you have 2-dimensional, it's going to be some sort of E Mulliken symbol, 3-dimensional T, G, and then H for 3, 4, and 5-dimensional dimensionalities. Okay. Then we're going to add a subscript 1 and 2. And those are going to be attached to the A's and B's. You saw previously we had A1 and A2. What is the difference between those? That's whether or not you are symmetric or anti-symmetric with respect to a C2 that's perpendicular to the principal axis, or if you don't have a perpendicular C2, like we didn't for C3, you only have perpendicular ones for D point groups, to a sigma V. Okay, so let's go back and look at this. Why is this one called A1? Well, we didn't have a perpendicular C2. Okay, why is it called A? First of all, it's called A because there's a 1 dimension here. Could be called B, but why is it not called B? Because this is a positive one, and that's the primary rotation axis. So both of these are called A because you have positive 1 here. Now you look for perpendicular C2. Well, there's no C2s in this point group, but there is a sigma. Okay, so we look at the sigma V. Sigma V was symmetric here. It's a 1, so we put a subscript 1. Here it's anti-symmetric, so we put a -1. So it's -1, so we put a subscript 2, so it's A2. So that's how that works. Again, it's really easy to follow. You just look at the rules, and you can look at the character table to come up with these patterns. You'll also see some of the character tables have Mulliken symbols with primes or double primes. Those are with point groups that have a sigma H. And so if you have something symmetric to it, you're going to put a prime. And if you have something anti-symmetric to the sigma H, you're going to put a double prime. G's and U's, this one we'll end up using a lot. And this signifies symmetry with respect to inversion. So again, for C3V, the character table we just looked like, we don't have an inversion symmetry element, so we don't have G's or U's. But if we did, the ones that were symmetric, i.e. a 1 character, we give a G. That stands for gerade. It's a German word. And then U, ungerade, that would stand for anti-symmetric, being -1 with respect to inversion. So those are the rules. It might look like a lot right now, but you'll very quickly get a feel for it as you look at more of these character tables. And there really aren't that many permutations. So it'll quickly become very straightforward.